Good morning, everybody. So we're ready for today's seminar, our DI seminar, DinAmicI seminar. So today the speaker is Paolo Giulietti from the University of Pisa, which is an old friend of our group. And he will talk about infinite mixing for accessible skew products. As usual, if you have questions, you can just turn on your microphone and ask the question or write it in the chat, and I will ask the question to the speaker. So please, Paolo.
Hi, everybody. So I would like to say thanks to DinAmicI for giving me the possibility to talk a little bit about infinite mixing for accessible skew products. I will try to be brief because we are running a little late. And so the first thing I want to say is that what I'm going to talk about, let me know, first of all, let me know if you can hear me fine.
Yeah, no problem.
Okay, so the first thing I want to say is that what I'm going to talk about is joint work with Andy Hammerling and Davide Ravotti, both from Monash University. And you can find the latest version on arXiv at the link. So the first thing which I want to talk about, which I want to say is that in principle, uniformly dynamical, uniformly hyperbolic systems are better understood, let's say, than partially hyperbolic systems. And so in the last 20 years, there has been a collective effort, I would say, to understand a little bit better partially hyperbolic system. The first and probably easiest example of the prototype of such system is the following. You take A to be a matrix in SL2 with determinant 1, and then you have a roof function, let's say, or to call it the function R from T2 to T. We suppose it to be smooth, not to discuss regularity, but as long as the regularity is high, we can forget about the issue. And the transformation F, which depends from R, maps X and T to AX, so it acts as the cat map, let's say, on the base, and takes T and shifts it by R of X on the second component. Roughly, I would say that if R is generic, so it must not be homologous or constant or other stuff of the like, then Ft is well known to be ergodic and mixing. So this the ergodicity goes back at least to 74-75 by the work of Breen and Pesin, and mixing goes at least back to Burns and Wilkinson from 99. But of course, there are lots of systems which are similar to this one, and to which we like to discuss the properties and then go back to those two results. The first thing which comes to mind that actually is very, very easy is the following. So suppose that you want to study the same system, but now your second component doesn't act on the torus, so it's not on T, but it's on the entire R. So your R maps takes values on the torus, but then maps to the entire line. And so what do we do? So this seems a very trivial question to begin with, but it's a lot more complicated than it looks like. So it is well known that as far as ergodicity goes, when the measure which you have on the real line is Lebesgue, then you can discuss ergodicity in the usual term. But as soon as you start talking about mixing, lots of weird things happen. In particular, let me start by the following for the people which are not familiar with the infinite ergodic theory nuances. And the first thing which I want to say is the following. So in general, when your measure is finite, you have Birkhoff theorem. This is a very simple example of what goes right and what goes wrong. So if X, mu, and T is a measure preserving system and the measure is finite, then for any phi which belongs to L1 of mu, it holds for almost every X the convergence of Birkhoff ergodic theorem. It is clear, even if one doesn't know the theory, that if one replaces mu of X with an infinite quantity, then the right-hand side is not so useful anymore. And in fact, one can say a lot more. So there is a theorem which goes back to Aronson, which says that if you have a measure preserving system, something happened. Okay, if you have a measure preserving system with the infinite measure, with the measure to be infinite, and suppose you have a sequence of positive real number an, then for every phi in L1 mu, such which is positive and such that the integral is positive, then the limit sup and lim inf of such sequences is either infinite or zero, of course, almost everywhere with the respect to x. This means that the usual knowledge of Birkhoff-ergodic theorem goes to zero or to infinity, and it's not as useful as it used to be. So, in particular, let me say one more thing in this sense. So, what about mixing? So, if the measure which is preserved is finite, then one can happily use the usually custom definition, which says that the measure of mu composite transformation multiplied by the measure of B tends to mu of A times mu B, as long as A and B are finite sets. As long as you start working with the infinite measure theory, then this definition, as soon as you look at it for more than 5 minutes, it becomes useless. And then one looks for a suitable replacement of this notion of mixing. So one reasonable option which appeared many years ago was so-called rational mixing. So rational mixing corresponds to the existence of a scaling rate, rho n, such that the limit of rho n of the measure mu of of A composed n times B, or it's equal to mu A times mu B, or equivalently, if f and g are local observable, which means they're locally supported function, then the measure of f composed n multiplied by g scaled by rho n converges to mu f and mu g. There is an extensive bibliography about ways of replacing mixing notion in infinite measure theory, and starting from Hopf, going to Krickenberg, who played the central role, and in recent times by Aronson, Thaler, Isola Belmul, Teresius, Weimüller, Lenci, Arbieto Markarian, and Pacifico Soares, and I'm sure I'm missing other as well who worked in the field. I want to focus on one of them, which seemed particularly useful in the last, say, 15 years or so. So it takes the physicist point of view. It's called global local mixing, and it goes back at least to physicists like Van Hove and Fischer, and Ruel, who worked when they were working in statistical mechanics, and they were forced to do infinite volume limits. For them, the idea of global observable was the fact that you need to explore the entire phase space as much as possible. This definition of this, say, working definition of infinite volume limits was formalized and put forward by Lenci in 2010 under the name global local mixing, and it has been used ever since in a variety of situations. Let's say random walk, mechanical systems, systems which have an indifferent fixed point, and so on and so on and so forth. So let me talk a little bit about it. So what happens is the following: if T, your transformation from R to R, preserves an infinite measure, which is absolutely continuous with respect to the bag, a global observable is any phi which belongs to L infinity of mu, for which it exists the average for R that goes to infinity of 1/2R of the integral on the entire minus r of your observable phi with respect to the mu. And I would call local observable any psi which is in L1 of mu. The basic idea is that one can replace the definition which we are used to, accustomed to, of mixing between observable by pairing a global observable and a local observable. What does that mean? It means that if you are looking at your system for sufficiently long time, and your global observable should be able to cover or to look at a very large portion of the phase space. It turns out that this definition is particularly useful. In particular, it is useful when one tries to discuss so-called quantitative mixing. If we want to investigate how fast is the convergence to such limit for our system, then we take A as before, and we let R to be smooth with zero average, and we study f of R as the action of A on the base and T plus Rx on the fiber. So if my R function, so the main result which I want to talk about is the following. It is from 2020, and it goes like this: if R is generic and my local observable is C infinity and compactly supported, because this is what I want for it to be local observable, then I have, let's say a dichotomy. If my phi belongs to C2, if it is periodic, then my transformation FR is rapidly mixing. In particularly for every k, which belongs to n, there exists a constant ck, which depends constant k, which depends also from the function phi and var p, which I'm using, such that the decay is bounded by ck n to the minus k. This is called the rapid mixing, and it's not the first time that it appears. It was actually used in a very strong sense by Dolgopiat in 2002, who studied circle extensions, which are systems of the type which I talked of the systems which I discussed in the beginning of the talk. So the idea is that when my global observable it looks at the entire phase space, but is periodic, then the decay is close in spirit, is akin to what you would see if you were looking at circle extension. On the other hand, if my global observable belongs to infinity, but is now an element of W1, which is the Sobolev space, the usual Sobolev space, which means it's a space which the function is in L2, and such that the derivative is in L2. And sorry, that's a union, but should be an intersection. And phi also belongs to an LP spaces. Then for any epsilon, the decay is optimally bounded by n 1 over 2 p plus epsilon. So there is a mistake which I can correct on the spot, because there should be a minus here in front. Oops. Sorry. No, it's okay. There should be a minus in front. Yes. So then for any epsilon, the decay is bounded by C to the k n to the minus 1 to the p plus epsilon. So the decay is still the function, the correlations are still decay. We have a quantitative estimate, but what we observe is that bounded by 1/2. So the main argument, which actually gives us this kind of result, is so-called accessibility. So accessibility, let me talk about it a little bit. Accessibility will be discussed later on. It describes how you go from one point to another point in the same in the phase space by following bits of stable and unstable manifold. So before going to before discussing accessibility and the idea of the proofs and the element of the proofs for this result, I want to show and discuss a little bit a series of numerical investigations for this kind of results, because investigating dynamical systems, especially when the measure preserved is infinite, require a series of ideas and tricks from the numerical point of view, which are non-trivial and that help us understand what goes on. So the first two slides which I want to talk about are what you see. And on the left, the system which is simulated is the same. As the base, I've chosen the cut map base. As my R function, I chose once a function which is periodic, which helps in the computation. And in blue, I choose a function which is non-periodic. In black, what I call the baseline is a system which has the same function on the fiber, but on the base map as a random map. Instead of using the cut map or any element of ASL, I used just noise. So basically, from one iteration to the other, I completely update the map with noisy points. So what do you see and what do you expect? So both in the left and the right, what you see is that the black lines, which are the ones which are constructed, which are constructed using the random dynamics, decay faster than the dynamics which use the real dynamic in the base. And as one would expect, because it's easier to kill finite Fourier modes than infinite Fourier modes, then what happens is that the red dots are most of the times, when they are not seen, you can see them, right, are below the blue dots, which means that periodic objects, when we do this analysis, are actually helping us in doing, are actually periodic elements, accordingly to also what I've said before, decay faster with respect to non-periodic ones. So I want to say that if one tries to do the simulation on this kind of infinite system, one one element of disturbance is given by the fact that you want to integrate, you want to explore the entire phase space on the fiber. Of course, this requires as a fundamental computational element that you decide how dense is the object, how dense is the number of points or the set of points that you want to investigate on the real line. Because obviously, from numerically, you cannot investigate all of it. So you have to choose a density and then stretch it as much as you can toward infinity. And all the simulations, as you can see, are very, very sensitive from the density of the fiber grid. The denser you take it, the better is your approximation. But of course, this requires a lot more time, and you are forced to have very, very, very few iterations. Again, what we see here is that the black dots, when the fiber is not dense enough, behave in a rather different way than respect to the other drawing. In fact, what we are just seeing is that I choose two observables and a grid for the fiber, which is not sufficiently refined to show my behavior. The next experiment actually is an example of what goes wrong if you do your computations not blindly, but if you let me say, if you hope that there is a cheap equivalent of the theorems that we proved. So this is somehow longish run, which means that this is the number of iterates, and actually I could make it go for longer times, but then the picture doesn't change too much anymore. What happens is that I've chose periodic and non-periodic R function in a slightly different way, and they are still zero average. But what happens is that as long as I can run my system, the decay is almost non-present. If I'm lucky, until some point in which then it starts becoming apparent. What happens is that if I'm very close to a resonance for my system, then the decay is very wrong. The decay is very slow. Moreover, what happens is that in the choice of my base and in the way I deal with the base grid, I can choose points which are very close or are shadowing an orbit for my transformation A. And this actually is able to kill for a very long time any decay of correlation which I'm trying to observe. This is something which has to be kept in mind if one wants to investigate numerically the decay of correlation in the sense of what I discussed in the theorem. So now, as we've seen that from the computational point of view, it's very hard to observe the behavior which we want to study, I want to go back to my dynamics. So the first step, which I want to discuss a bit, is the reduction step. So in the beginning, I produced my transformation was f of r x and t, and then I had ax and t plus rx. So the first step which we do to actually carry on the proof is to reduce these dynamics to the symbolic to his symbolic counterpart by the use of Markov partition. That means that we are investigating a two-sided shift on the base, which is topological mixing, and now my R is Lipschitz, and with the zero average with respect to invariant Gibbs measure mu. So this reduction helps a lot in producing the results that we've seen, but in principle, we will see later on that it has limitations, and one could avoid it completely if one produces distributional analogs of the objects which we will discuss. So, as one should discuss all the words in the title, I have to discuss a little bit what I mean by accessible. What I mean by accessible is that on X, which is my phase space, I can obviously define a distance which is inherited from the symbolic dynamics and the distance on the fiber itself. And then, of course, I can define stable and unstable set and their strong, stable and unstable counterparts. So what do I mean by strong, stable, or unstable set? I mean the elements of WS XT are the elements YS such that Y belongs to the stable manifold of X, and S minus T, the fiber, is the limit of the Rn of x, which is the Birkhoff sum, what is that goes to 0 to n of sigma I x, and I forgot the r. So once I take the Birkhoff sum of this element, then what I want is that the distance on the fiber is proportional to the Birkhoff sum of my element. Then what happens is that with this definition, which are actually quite natural from the symbolic setting, I inherit that xy is equal yy for sufficiently large y. This is because if you look at the future and you keep going, eventually by looking at the stable set, this is what you get. Moreover, since I'm still inheriting what I inherit from the symbolic dynamic again, is that the distance goes to 0 exponentially fast. Of course, as the distance, I took the distance above. The same thing happens analogously if I try to define the unstable y of s. So once I decided I introduced some definition about the objects which I have to discuss to define accessibility, I can actually introduce and say what accessible means. So first of all, accessibility is a very powerful tool. In principle, it's interesting to check to check out and understand a little bit about it, because it's a very strong framework to deal with the partially hyperbolic system. The idea which is contained in accessibility and being accessible is the following. So a stable and unstable path is a sequence of points such that each pair of successive points are reached via bits of stable and unstable manifold. So it means that basically I can go from one point to the next, either by following WS or by following WU, or going back to again WS, and so on and so forth. So in particular, we say that F, our transformation, is accessible if for every two pairs there is a path between them. This is a very strong topological property, in the sense that allows, once it is established, it has a cascade of effect. It has a number of results, and there is an entire research program, which you can read in the references which I suggested, which tries to turn accessibility, which is a generic property in some sense, into something which we can use in a quantitative way. And our results is an example of such idea. So once I discussed accessibility, I have to introduce a little bit better what we mean by global observable. So if eta is a complex measure on the entire fiber R, and let TV be its total variation. So the total variation is just the supremum of the variation when the set E goes to infinity with respect to functions which are measurable and have norm 1. So the key fact, which is actually one of the two things which I think it's worth noticing, is that if my measure has finite total variation, then it's by Fourier integral transform can be written in this way. So you can write that this transform is the integral over R of e to the minus itx xi eta with respect to dxi, and this element belongs to L infinity. So this is a very it's a good class of global observables which we'll use, and the set A, the set of A of such transform, is a Banach algebra once we choose as its norm the total variation norm. In particularly in this class A, we can find the Schwarz function, W1 function of R, which is what I discussed before, Lipschitz and periodic and functions, and also let's say stranger, more exotic function. For example, you can put infinite products of sine and cosine function. You can use positive definite functions. What the main reason for us to use global observable of this following is the following fact. So there has been a discussion along the year which was connected to the infinite mixing definitions, or of which are and what are good observables or good ways of replacing the definition. And I don't have a definite answer to that, but I can say that global observable which arise in this way as infinite average can be seen as spectral measures at zero. Being spectral measures at zero, they are basically objects which we understand somehow very well, and are all the theory which we produce can be translated already in another language. So they make very fairly good candidates to be good observable. In particular, what happened is that what I just defined is really the measure at zero, the spectral measure at zero. Also, as I said before, the elements which belong to the class A, which might seem very little bit artificial at first, but once you start working with them, you remember a theorem by Buckner, which goes back at least to the 70s, and which says that an element of the class A belongs to the class A if and only if is a linear combination of continuous positive definite functions. Positive definite functions are functions such that for any 2 points and for any 2 real points and any 2 complex points, their linear combination is still positive. It's a very powerful tool and allows us to do the following pairing. So rather than looking at local observable and global observable directly as function on the phase space, we see, so in principle, local observable are functions of 2 variables, right? So they are functions of the symbolic dynamics and of the T, of the fiber. And so and global observables as well. So instead of seeing them as functions of 2 variables, we see them functionals. And these help us in the following sense. So for us, local observables are Lipschitz functions, psi, which maps the symbolic dynamics to the space of Schwarz function. And global observable are Lipschitz functions, which maps the symbolic space to our class A. So there are two stars in here, because there are also there is also a minor technical condition on the global observable G's, which is tied to the fact that you really want to use Bock theorem and not another results. But for the sake of this presentation, you can think of them really just as Lipschitz function from the symbolic space to the set A. In particular, how do we use the construction that we propose? So you're given your global observable var pi, and then you see it as the Fourier transform at the point x of a measure theta, of a measure eta. This can be done via Bockner theorem. And then what happened is that the infinite volume measure, which we defined, can be seen as this is the measure, the original measure of the system. This mu comes from the symbolic dynamic. And this is translating my global observable phi. So we have seen that the infinite average in this way can be actually described by the spectral measure at zero. And what happened to around zero is obviously fundamental, and it's actually can be seen as what we call a low frequency mode. So basically, low frequency mode are actually the same measure computed at x, but on a larger sets around zero. So this is how you pair local and global observable, and why is it important to look at the spectral measure at zero and what happen around it. So the main theorem, and the reason for me to introduce the low frequency mode is hidden in this theorem, which says the following. So suppose that f of r, I forgot the function, being accessible skew product, if var p times c belongs to global times local observable, then for any k and for epsilon, there exists a c, positive c, such that decay is bounded by the constant c. Then you have the low frequency mode, and then you have the part which decay as n to the minus k. As it says below, the decay is polynomial unless you can kill the low frequency mode. In the case, it becomes super polynomial. So one can see the theorem about being periodic, the dichotomy about being periodic or non-periodic, as a theorem in which one can kill or not kill the low frequency modes. If one can see this kind of statement as the usual, say not another flavor, but another way of appearing of the fact that in order to have faster decay of correlation, there are a family of functionals which have to be zero for one to observe such behavior. Here, in our description, these functionals are tied to low frequency mode rather than to say polycot resonances of the transfer operator. But the idea is still morally the same. So as a last slide, I want to discuss a little bit. The sketch of the proof. So, as usual, when one starts with the cut map, then one first ends up with a two-sided shifts, and then one has to turn it into a one-sided shift. This requires actually turning accessibility, the fact that you can follow paths to stable and unstable, into so-called collapsed accessibility. This is actually a rather technical, say, part of the work, which amounts of saying that the following: if you have a point, if you have 2 points which you connected to bits of stable manifold, and then you had here an unstable manifold which connected them, you can think about the fact that when you turn from from two-sided shift to one-sided shift, in some sense you're killing or completely destroying this part. You're getting rid of the unstable part. So what you really want to say is that if you apply sufficiently many iterates, this part and these parts they're not going to touch, but they're getting close enough so that you can disregard this small jump in here as a small error. So this is a very brief sketch of how you turn accessibility into collapse accessibility. And the other part of the argument, which is also somehow a little bit more technical to deal with, is it requires studying the transfer operator and turning into a twisted transfer operator. So the only thing I want to say about this part is the formula computation, which could become useful if you're interested in this kind of problems. So the first integral which you see is you have your global observable on which the dynamics is acting because you are composing with Fn, and then you have this belongs to local, and this belongs to global observables. And then, as usual, what happens is that you, as usual in transfer operator theory, by duality, you define the transfer operator, you ask the transfer operator acts on the local part, leaving the global observable in some sense free to be used. And so what happens is that your global observable, which is now here by itself, can be turned by previous identification and by the discussion into this into the measure which corresponds to it. And then, of course, the price which you pay to do this business is that instead of looking at the transfer operator and acting on the global, on the local variable, on the local observable, you have to study the Fourier transform of the transfer operator acting on such a local object, on such a local observable. Once you have this formal computation worked out, and it obviously makes sense, then one is left with the task of splitting the integrals and studying them in 3 blocks. So this is something which always happens when you try to turn accessibility or any other kind of pairing of manifolds into quantitative estimate. So how do you split them? So you have 0. So you choose this psi is equal 0 because for 0, then what you really have is that you're studying. You're not studying a twisted transfer operator, but you're studying the standard transfer operator. Then you cut your xi from up to -1/2, and then you cut your xi for in a bit greater than 1/2, and you treat them in very different ways. So the low frequencies, which are what we call LF, are then studied and treated by perturbation, as perturbation analysis, because so they are close to 0. And so the transfer operator of this for real psi small magnitude can be seen as a perturbation of the transfer operator at 0. And high frequencies are then treated by accessibility. What I mean by treating them by accessibility is that you can use accessibility to construct an estimate which implies that your integral in this region is very small, basically due to cancellation. This does not come as a surprise because if you look at the drawing which I've just made a little before, what happens is that basically I can construct. This is my fiber. This is my point x and t. And this is my point y and s. And what means is that for very high frequencies, once I consider this as some kind of loop, then cancellation in the integrals appear, and then the integral has a very small absolute value. And this is morally what you have to do in order to show the estimates on the decay of correlations. And this is all I wanted to say.
Okay, thank you. So let me just clap for all the audience. Cool. So I think we have a lot of time for questions, comments.
Sure, go ahead. So,
oh, is Oliver maybe raising a hand?
Yes, I raised my hand. Maybe I should have just started talking.
Yeah, you can. You could do that. Yes,
I was. Yeah, thanks. Can I ask? So I like that it was turn on using accessibility. I was curious if I understood correctly. So the accessibility is used to prove these rates of mixing. One thing I wanted to ask is, I guess you know that sometimes you can't get these rates of mixing, and also how that relates to not having accessibility. And also, is it possible that accessibility is equivalent to what happens in the fiber not being cohomologous to a piecewise constant? And also, is there some possible equivalence with this to mixing?
Oliver, slow down. So there are two parts. So the first part, which I understood of your question, is how does accessibility relates to being not being cohomologous to a constant?
Yes, please.
And the other part, which I didn't, so you asked something else about, you asked another question as well.
Equivalence with mixing.
No, you said something in case things don't go right, when the decay is not so fast.
Yes. What can you say about the requirement of the accessibility assumption?
So there are two sides of the story, which goes the following. So since this is what it was hidden in the warning, in principle. So when you turn your system from AX to the symbolic counterpart, basically what you are doing is that you are saying that either your function R is cohomologous to a constant and your system is not accessible, or your function R is not cohomologous to a constant and your system is accessible. This is actually, there is an appendix in which we do essentially this kind of discussion. So discussion goes like this, and it's easy to see in the following case. Instead of using the point is the following, that you can use other objects beside AX, beside the linear matrix. You can use any kind of Anosov matrix on the basis, right? But then the Markov partition makes the discussion a little bit more complicated. But if you just take AX, then stable and unstable bits are just straight lines. And being accessible just means that you can connect different bits of the Markov partition, which you can always do. And of course, that means that you are not cohomologous to constant, because if you are cohomologous to constant, then going around just means that it's zero, and then you are done. So this is the first question. And the second question is also very interesting, because let me go back to this. Sorry, let me, here you go. I hope I'm still sharing my screen. So
yes, you are.
Yes, so what you ask is basically hidden in this word, optimally bounded. So what happened is that you can choose observable. You can actually produce explicit examples of observables which do not decay faster than 1/2. So this is why the result is sharp, and it has to do with the fact basically that on your fiber, the displacement is governed by the R itself. It's not by the dynamics which takes on the base. This is also the reason for me to do the numerical example in which you, on the base, you put a completely random thing. I mean, on the base, instead of putting AX, you can put something which is completely random. That you wish that would help you, but it doesn't. So this is why also Dolgopiat says that basically the decay is it's rapid mixing, but it's it cannot go faster than that. It cannot be in general exponentially mixing. You just don't make it so far. And the last comment which I want to make is that this is why I think it's important to understand accessibility a little bit better in a quantitative setting, is that basically you to prove decay of correlations, you want to, in partially hyperbolic system, you use dominated convergence, dominated splittings, or accessibility, or a combination of the two techniques. So you're free to choose which one you want. And it's not clear to me when one technique is better than the other and when one works and the other doesn't. And so, but in principle, you could turn both of them, dominated splitting and accessibility, into quantitative estimates. So I hope I was clear.
Thank you. Thanks. Can I, ask very quickly, can you remind me what the collapsed accessibility was?
Yes. So collapsed accessibility, in a nutshell, means that you turned from two-sided to one-sided subshift, and so you don't have anymore the unstable manifold, right?
I see.
Because when you move from two-sided to one-sided, eventually, if 2 points are the same and you keep shifting them, then they actually really coincide. They are the same point. So basically, you don't have anymore the unstable manifold, and you have to deal with it. There is nothing you can do about it. But this is how to say? This is something that we are accustomed to. Because if you take 2 points which are very far apart, then you wait some time, then they are close, but there might still be some distance between them, which you close by an unstable manifold. Then you say, well, I'm unlucky, I just need to wait longer and get them as close as I want to. So this actually is the reason is one of the reasons for the epsilon for an epsilon, the decay is bounded by the plus epsilon. Because basically you have to close this loop, and this loop is small as you like, but it's there. You cannot avoid it.
Fantastic, thanks. It's clear.
Okay, so it seems we have another question, maybe by John Aronson.
Hi, John.
Hi, nice to see you all.
How's life?
Yeah, great. I mean, I'm out of lockdown and everything. Everybody else is in lockdown, but I just choose to be out, so it's okay. So I don't know. I was kind of zipping between the YouTube and the Zoom because I had something that I didn't have the right password, so maybe I missed it. So did you have some kind of digital way or symbolic way to prove what do you call it, accessibility? And what are the examples? How do you do it, and what are the examples?
So a digital way to prove accessibility. Accessibility. Yeah. Yes. So what are the examples? So the best way to prove accessibility is, to be honest, is to know that you can find it. So this goes back to the question also someone asked by Oliver, which is the following: if you know that the function which you chose as R, this R over here,
yeah.
If you know that is not homologous to a constant, and with A you choose the cut map, then basically what you're doing, you're using Markov partitions, right?
Yeah.
And so accessibility just means that you can you can follow straight lines through the elements of your Markov partition, which you can always do. So in the case of rigid things, it is very easy to see that this is rigid. I mean, in the case of linear maps, it's very easy to see that this when this happens and when this does not happen before turning to symbolic dynamics. When there is the map you're using is not A, but say you replace. Let me see what the way is. Replace A by say an annus of F, X,
yeah.
Then you have to be more careful. But what you want to do in principle is follow the same route, which means that you want to conjugate your system to its linear part, and then go from there. But this is what I was hiding, saying that you want your R to be smooth, because if you take R with too little regularity, then you cannot do that. But if you take your R to be smooth, then you can still conjugate effectively the two dynamics. Let me see.
So in the symbolic situation, you're saying that R should not be, if A is the shift or something,
Yes, yes,
some
yes.
subshift, a Markov subshift, then R just should not be cohomologous to a constant, and that's enough.
Basically, this is actually the truth. Yes, and this is how you prove accessibility.
But you're on the reals, so you could be taking values and you could be cohomologous to some integer value function.
The problem is that if you are cohomologous to so let me just make a very quick proof, which I think helps. So suppose this is the fiber, your fiber R, your real line.
Yeah.
And you're going around in a loop, and you have an integer. Then in principle you can cut your bits in 4 bits, and then you keep going around, right?
Yeah.
And so eventually, basically, what happened is that either you were already homologous to a constant, or you're fine. So there is not too much. So in the symbolic dynamic system, there is not too much that can go wrong. But if you start with something which is which say, for example, if you try to let me just answer you in a different sense. If you start with something which is higher dimensional, then things can really go wrong, because there is no way you can do this kind of proof anymore. I mean, if instead of having a fiber which is just R, you have a fiber which is R squared, then who knows?
Yeah. Okay. Okay. Fine. As I take a look at it.
Okay. So
Thanks.
just asking if there are more questions. Okay, maybe not. So I think we can then thank Paolo again. So let me just clap.